UniFirst and Sullivan Training Systems. Uniforms that work. Training that works. For people who work.
Okay, let's talk about voltage drop. Let's try to figure out exactly what voltage drop is. It's very important. You need to understand it. And reading voltage drop is not the same as reading voltage. There's a difference in the way you hook the meter up and a difference in the expectations. Okay? Voltage drops only happen when current flows. If current's flowing, there will be a voltage drop, good or bad. All right, let's look at a quick and dirty circuit here. Two resistors, 50 ohms each, 12 volts, 1245 applied. Let's turn the switch on. All right. So I got about 12.45 coming into the board, which means we're going to have about 12.45 coming into the first resistor. Well, the two resistors are the same. They're both 50 ohms. So if we read the voltage coming into the first resistor, it's going to be our 1245. But the voltage coming out of the first resistor is going to be about half because the two resistors are the same and they drop the same amount. When we come out on ground, there shouldn't be anything more than millivolts. So the first resistor drops about 6.2. The second resistor drops about 6.23, and you add those two up and they equal 12, which means there's nothing left over. All the voltage drops have to add up to equal source voltage. In other words, all the voltage has to go away. You can't not have it go away. It has to go away. Okay? So if all the voltage has to go away from positive post to negative post of the battery, if you think about it as a circle, which is why it's called a circuit, under normal conditions, the only components that should actually use energy, that should drop voltage, that should do something, are the components that do something. So anything that actually does something and turns electricity or voltage or energy into something else that's all that should be using voltage. So a horn or a light or a solenoid, the components that actually do things should use energy and nothing else should. If anything other than a load component uses energy, it's wrong. Okay, now you can say a resistor and a speed control, but that's slightly different, but that's not a problem, that's normal. But wires, connections, and switches, or anything else in the circuit other than the load uses voltage, it's a problem. And if one of these uses voltage, then what's happening is there won't be enough energy left over to operate the thing that's really supposed to be doing something. So headlights are dim, motors run slowly. That's what the result is if I added resistance in the circuit. Okay, now let's look at another quick and dirty circuit here. We'll put the two resistors in. Okay, but now I'm going to put a light bulb in parallel with those two resistors. Now, by the way, you need to understand something. There's no such thing as a parallel circuit. It's parallel circuits. So don't ever say parallel circuit. There's no such thing. Okay? So this light bulb is bright because it's tapped in front of the two resistors where the voltage is 1245, like I showed you earlier. Okay? So the bulb works normally. Those resistors don't do anything to this bulb because they are a parallel path. But the bulb has no added resistance. It's simply tapped in front of those two resistors because it's in parallel. So the bulb is working in this particular case because it's simply tapped into a 12-volt supply and it's working in conjunction with those two resistors. All right, here's that system on the training board. All right, notice ghost voltage, zero voltage. I'm flipping the leads around to show you ghost, putting the leads together to show you zero. And this is what I just drew. Okay, this bulb is in parallel with those two resistors. This is a series parallel system. If we read the voltage and load it at the power supply, it's 12 and stays 12. If we read the voltage at the fuse and load it, we get 1240, 1280. It drops to 1240. That's normal. Now notice that the voltage coming out of the switch is straight zeros. All right, 0, 0, 0. Why? That's because that wire is touching ground and there's no current flow. Okay, so the meter's showing you that it's touching ground. That's important. Notice that I'm flipping these leads around trying to make the meter read ghost voltage. All right, well, here's the 1257 coming into the bulb. But notice that it's 1265 at the board and 1255 at the bulb. That tenth of a volt is important. All right, and what did we do on the math? Well, the first resistor dropped about half, the second resistor dropped about half, and now on ground, we're reading millivolts, just a few tiny little millivolts. Full system in, half of it's gone, and now the other half is gone, and we're down to millivolts. All right, now look at the individual drops. Here, these are the actual drops. 6.25 on the first resistor and 6.2. That adds up to 12.45. All right, 625, and the full system voltage is about 1254. And what's coming into the board, coming into the switch is 1247. Well, that's almost perfect. All right, 1244. And then you take away 624 and 620, you get 0. So all of the energy goes away. All right, now let me show you how this works if the bulb is working. All right, this is something that everybody pretty much understands. Okay, when you read the system voltage, what you do with this tool, this Load Pro leads, is you load the circuit, and when you load the circuit, if the voltage stays up, then there is no voltage drop, and the circuit's working. The wire's good. Okay. All right, here's another drawing, but I'm going to put a bulb behind the two resistors. Notice there's still the 250s, but look what happens. The voltage drops change slightly, but they still add up to 12. 5 plus 5 plus 2 equals 12. The bulb's only getting about 2, so it's dim, and the two resistors are dropping about 5. Okay, so flip the switch on. Notice the bulb is now attached with the purple wire to the back of the two resistors. We still have 1255 coming in, but now we've lost about 5. Now we've lost another 5, and we're down to about 2.5. Okay, the bulb's working. If you just barely look at it, it's working, but not much. Okay, so what's going on here with the bulb? What's going on? Why is that bulb not working? Why do those voltage drops, why do they show up the way they do? All right, so let's take a basic circuit here, just a basic single switch, single load circuit, fuel solenoid switch. Okay, all right. On the board earlier, you saw a bunch of resistors in series, but that's very unusual. Okay, that's just for testing. Under normal circumstances, there will only be one load per circuit, and it drops everything. In other words, one solenoid drops all 12. Okay, we turn the circuit on here, and let's just pick a number. Let's say we start at 1273. It's a little high, I guess, but that's okay. When we get to the switch, it's still 1273. When we get to the solenoid, it's still 1273. But then it drops, boom, to 0. Okay? That's normal. This is a normal voltage drop. 12, 12, 12, 12, 12, boom, 0. Okay? So this is important to understand. Voltage on ground with the switch closed is evil. It should not be there. It's immediate indication that there's a problem on the ground. Voltage on ground means a problem on the ground if the switch is closed. All right, so let's put corrosion in the circuit here, in a connector. Let's put a little green crud in the connector here. Well, it's going to stay 1273 all the way out to the corrosion, but then, boop, we drop a little bit. And let's just say for the sake of argument that we've only got 724 left over coming out of that rust, or that oxide, so when it hits the coil, it's only got 724. Well, that's not enough pressure to make the coil work, or it makes the coil work badly. All right, so the good voltage drop in a normal circuit is that everything drops 0 except for the load, which should drop everything. Okay, but in a bad, let me do the math here real quick. Hold on, Carrie. Okay. In a bad scenario, in a wrong scenario, if the connector is using voltage, in this case it's dropping about 549, it's leaving the 724. So the coil is only getting the 724 and the coil works badly. Okay? Notice though that just like the training board, the connector voltage and the coil voltage both add up to system voltage. This is a critical law you must remember. It's called Kirchhoff's law. Okay? So here we are again. Change the resistors to 100 ohms, but it's still basically the same idea. So now 1260 coming in, 686 coming out, and 1 left over. Okay? So they're dropping about 5.5 each. But notice here that if I jump across the 2 resistors, which is the only thing required to fix the problem here, the bulb works brightly. So no tricks. 2 resistors, dropping voltage, bulb is dim. Jump the resistors, bulb works. Resistor 1, 5.71. Resistor 2, 5.86. So about 5.7 and about 5.8. Well, the 2 numbers are the same because the 2 resistors are the same. But if you add them up, look what you get. Okay? You get a 5.73 volt drop across the first one, about 5.86, and then about 1 left over. And that adds up to just about 1260. So once again, Kirchhoff's law has to work. All right, but let's look at what happens in the real world. In the real world, we don't have this nice, neat little scenario, okay? In the real world, you've got a bulb in a socket, and you pull the bulb out in order to make the test, which is what the manufacturer tells you. This could be an ECM. This could be ECM power. It doesn't matter. The problem is, as soon as you pull the bulb out, you've opened the circuit. Well, how much current's flowing? None. And what was the requirement for a voltage drop? You had to have current flow, okay? So in the top circuit, the reason that there's a 2 volt drop there is because the circuit's closed and complete and current's flowing. The bulbs are getting hot. The resistors are getting hot, okay? So the top circuit's working, bottom circuit's not. Well, the reality is that if the bottom circuit's not working because you've opened the circuit to take the reading, then the 1245 is going to show up, and that's going to throw you off. You're going to go, hey, I got 1245. I must need a new bulb, or I must need an ECM, or I must need a new coil, or I must need a new clutch, or I must need a new motor. But there will be no voltage drops if current isn't flowing, right? So as soon as you open the circuit to make your test, boom, you're screwed. So this 50 ohm resistor really isn't a 50 ohm resistor. Neither is that one. The truth is that if current's not flowing, you're not going to see what you need to see. So the critical reality of a voltage drop is, to see it, you must have current flowing. Okay? Now, watch what happens here. If I jump across these 2 resistors and take them out of the circuit, then the bulb works. All right? And we've already done this math, but let me show you again. All right? We've got 1246 coming in, 681 coming out, and about a volt coming to the bulb. Well, the bulb is not really working very well. So that's pretty obvious. And the reason it's not is because by the time you get to the bulb, there's only a volt left. Okay? Well, imagine what would happen if this was an ECM, all right? It can't work because the resistance is in the way. But only when current is flowing. Because now look what happens. Oh, there's that negative sign again. Cannot have a negative sign when you use these load pro leads. You have to have a positive number here. So we read full system voltage, but wait a minute. There's 2 resistors in the way. But look what happens when we load the circuit. We drop voltage. We get an instantaneous voltage drop because this resistor and this resistor aren't doing anything until the current flows, so the voltage is normal. We're just reading the battery voltage right now. Push the button, circuit turns on, voltage drops. We know we have a problem in the circuit. Okay? So it's dropping from 1281 to about 1.3. Well, look, there's 000 drop across this one because it's not doing anything until you put the bulb in and the voltage drop comes back. But notice the bulb isn't lighting up, but it's still working. This is where people get so goofed up. The component's actually working, but not really, but just not much. And that's where the problem lies. The voltage is there until you plug it back in, and then the voltage goes away. In this case, there's a volt coming to the bulb, and you notice the bulb's not on. But as soon as we pull the bulb out, it goes back to full system voltage. This is where the manufacturer's instructions fail you, because it tells you if you have voltage, go to the next step. And when you get to the end, changing the part doesn't fix the problem. These leads make that problem go away.